Hello everyone, thanks for watching this video. I'm Rizzo, a PhD student advised by Dr. Wenye Wang in ECE Department of North Carolina State University. It's my great honor to present you our paper accepted by IEEE Infocom 2020. U-CIMAN, Uncover Spectrum and User Information in LTE Mobile Access Networks. In this paper, we design a new tool to measure spectrum tenancy and present the measurement results. Here goes the outline of my presentation. I will first introduce the background, motivation, and research questions. Then I present how we design and implement the spectrum measurement tool, U-CIMAN, followed by the measurement results, and lastly, the conclusion. This paper is motivated from two aspects. The first one is why we want to design the new tool, and the other is why we want to apply the tool to spectrum tenancy measurement. We propose U-CIMAN, which decodes and parses unencrypted control and data channels in LTE downlink. U-CIMAN is useful in that there are strong demands on the spectrum and user information revealed by the decoded protocol fields. When applied to spectrum measurement, U-CIMAN has many advantages over the traditional method. Spectrum and user information are essential for applications within mobile networks. For example, video streaming over wireless links need to adapt to different available bandwidths in the cell. When available bandwidth changes, the video server needs to know it and adapt to it by changing video quality. For peer discovery in device-to-device communication, mobile devices need to know the location of peers to save energy on peer discovery. Such information is known by the network side, but user devices and mobile applications can only infer them. User and spectrum information are also important for devices outside mobile systems. For example, IoT systems need to predict user trajectory to provide better location-based services. Secondary users would like to find the spectrum host to transmit their data. Currently, such information is obtained via different indirect methods, such as the trace analysis or the energy detection. Since spectrum and user information are well known by the network side, another way to obtain such information instead of inferring them is to sniff them over the air interface. The research questions are what information can be obtained in this way and how to achieve them in LTE system. To address these questions, we design and implement a tool, U-CIMAN, to decode both control and data channels. As far as we know, the data channel decoding is proposed for the first time, and we improve the existing methods for control channel decoding. One thing to notice is that U-CIMAN obtains spectrum and user information from unencrypted data fields. So it does not break LTE encryption. Thus, it should cause no security or privacy concerns. There are many potential applications for the protocol fields decoded by U-CIMAN, such as the examples presented in earlier slides. Among these applications, we choose to apply U-CIMAN to spectrum tenancy measurement. Due to the limitations of the current measurement method, currently, spectrum tenancy measurement is achieved by the energy detection method. The classical method measures the power spectral densities of radio bands of interest. This method is inaccurate in tenancy measurement, in that it measures power levels, which requires a threshold value to turn the readings into tenancy. Its measurement results also fail to satisfy needs of secondary users, since essential details, such as user location and traffic types associated with spectrum usage, cannot be detected. By measuring spectrum tenancy with U-CIMAN, users can overcome the limitations of the energy detection method. As shown in this figure, a secondary user wants to access some spectrum slices in the mobile bands. It first asks for spectrum holes. U-CIMAN tells the secondary user exact locations of those holes in the time spectrum grid, instead of the detected power levels. Besides, U-CIMAN decodes the user information associated with the spectrum usage, data fields related to user locations and traffic types. Secondary users need to know them due to the hidden terminal issues and different consequences of collisions with various traffic types. Based on the different services provided by U-CIMAN and the energy detection method, I believe this secondary user in the example will choose U-CIMAN. To apply U-CIMAN to spectrum tendency measurement, we need to answer two questions: how U-CIMAN measures spectrum tendency, and what are the measurement results and observations. The detailed answers will be revealed in later part of the presentation. To answer the question, we identify the LTE protocol fields that can serve this purpose, and decode and parse them. We measure the spectrum tendency of a commercial LTE cell with U-CIMAN, and the observations will be presented. There are two parts in the second section. The first part includes an introduction to LTE and the design of U-CIMAN. The second part is the implementation and the performance evaluation. Let's first look at the LTE protocol stack to see why U-CIMAN can decode without breaking LTE encryption. As we can see, LTE encrypts both control and data planes at PDCP layer, shown by the open blue logs and white boxes. Some data fields are left in clear text because they originate from layers below PDCP, like the ones highlighted by red boxes. Other messages that have to be in clear text happen before encryption setup. As we can see, most unencrypted messages and data fields end up in the shared data channel in the physical layer. Thus, sniffing is possible without breaking LTE encryption, and the key is the shared data channel. The first step to decoding downlink user data is to locate the spectrum resources, since they are shared among all users. The locations of spectrum slices carrying user data in the time frequency grid are assigned in the downlink control information, or DCIs, for both uplink and downlink. DCIs are in the downlink control channel, which takes the first 1, 2, or 3 OFDM symbols. Every millisecond, DCIs are transmitted to assign spectrum resources in the unit of resource blocks, RBs, which are half a millisecond by 180 kHz. The control channel region can be obtained after achieving downlink synchronization by decoding synchronization signals and the main broadcast messages which are not encrypted and transmitted at fixed positions. The takeaway is that DCIs point to user data, and the DCI region can be found by getting synchronized and decoding broadcast messages. This is the overall processing steps of U-CIMAN. First, the radio front gets downlink synchronized with an LTE base station using the synchronization signals and the broadcast messages. Because the control channel has fixed modulation coding scheme and MIMO mode, the symbols can be demodulated. Since there is no encryption for DCIs, U-CIMAN parses the DCI messages to obtain the information required for user data decoding. The DCI decoding adopts the method proposed in other papers, which has to consider the decoding as perfect, since RNTIs are not known, so the CRC checksum cannot be used as intended. RNTI is a temporary identifier of user devices in the physical layer. Key intermediate results, the RNTIs and TMs, are stored in lookup tables and forwarded as inputs to data channel decoding and the later decoding of control channels. TM is the multi-antenna mode. The main improvement of U-CIMAN is the decoding of data channels and the feedback of RNTI to improve the reliability of control channel decoding, different from the current DCI decoding, which cannot verify the correctness of RNTIs. The data channel decoding uses RNTIs as inputs and has valid checksum mechanisms, so that only correct RNTIs can result in successful decoding. The main decoding steps, the inputs and outputs, are illustrated in this page. By achieving downlink synchronization, the cell ID and the subframe number are decoded. Then U-CIMAN adopts existing methods to obtain RNTIs and DCIs by decoding other control channels. To decode user data, the first step is to locate them in the time frequency grid according to information parsed from DCIs. Then TM, or multi-antenna mode, is required to further undo the pre-coding and layer mapping. TM is configured in ciphered messages, so U-CIMAN tries all possible TM values corresponding to the DCI type, Possible TMs for one type of DCI are often very few. Then demodulation can be done according to the MCS parsed from DCIs. Lastly, the MAC code words of user data can be achieved after descrambling. If the user data decoding fails, then U-CIMAN knows the corresponding RNTI and DCI are incorrect. The key contributions of this design are proposing the data channel decoding and improving the existing control channel decoding by verifying the correctness of RNTIs. Data fields recorded by U-CIMAN are shown in this table. Spectrum tendency is indicated by the resource assignment, RA fields. There are three types of resource assignment in LTE, and RA1, 2, 3 are the parameters as specified in the standards. Time advance, or TA values, indicate the user locations, and the details will be introduced later. The packet sizes reflect the applications. This will be verified in the evaluation part later. Now let's look at the implementations and evaluation settings. In terms of hardware, U-CIMAN requires a computer and a USRP as the radio front. We implement the decoding and parsing of control and data channels in the user space of a Linux computer. Existing LTE routines are implemented by calling the functions provided by SRS LTE library. Convergence between baseband digital samples and analog radio waves are realized by the USRP. To evaluate the performance of U-CIMAN, we use two settings. The first one is measuring the spectrum tendency of an LTE network fully under our control, so we know the ground truth by accessing the log files. The second setting is measuring a commercial LTE cell that serves human users with realistic mobility. We first evaluate the decoding accuracy of U-CIMAN. We run 3 different applications, and the average decoding accuracy for both control and data channels are above 90%. Next, we show that distributions of packet sizes reflect the application under different traffic loads in the cell. Whether the cell traffic load is small or large, the 3 different applications have distinct packet size distributions. Now let's see how TA values reflect user mobility. Time advance, TA mechanism is for uplink synchronization in mobile networks. LTE max TA value is 1282, corresponding to radius of 100 kilometers. TA update is 6-bit, from 0 to 63. New TA value is the sum of original TA, TA update, and minus 31. The upper plot shows the TA value distribution of over 2,000 randomly chosen packets. As shown by the plot, most users do not move since TA update of 31 takes the largest percentage. The lower plot shows the percentage of packets having the same TA value in each hour. We can see that users in commute hours and lunchtime have high mobility since percentage of TA updates of 31 are low in those hours. Next, we present the observations on the spectrum tendency of a commercial LTE cell measured by U-CIMAN. The observations are from the time perspective and the frequency perspective. We first look at 3 metrics from the time perspective. They are measured per millisecond, but we look at the statistics aggregated hourly. The first metric is the size of the control channel. It can be 1, 2, or 3 OFDM symbols. It corresponds to the level of radio activities in the cell. We plot the total occurrence of different control channel sizes in each hour. For the other 2 metrics, the number of DCIs and occupied RBs, we show the rough distribution in each hour by plotting the mean, the 15th and the 85th percentiles, and the minimum and the maximum. From the first 3 plots, the 3 metrics show very similar daily trend, which has a stable low in early morning, then increases to a steady high value during the day. that lowers to another stable value in the evening. When examining the aggregated statistics in hourly scale, it seems that control channel size and the number of DCIs are highly correlated with spectrum tendency. However, when we correlate them at the millisecond time scale, the correlations are low, mostly below 0.5. Now let's look at what affects the frequency of occupied channels. The first three plots show that the hour of the day, packet sizes, and the TA values have no impacts on the frequency. For different hours, packet sizes, and TA values, the distribution of occupied channels look similar. However, when conditioning the distribution of MCS values on the channel occupancy, the distributions of MCS are obviously affected by whether the channel is occupied in the next time slot or not. Thus, the channel occupancy is related to the MCS in the previous time slot, but not affected by hours, packet sizes, or TA values. Now let's conclude the presentation. The sniffing tool U-CIMAN is able to decode and parse undeciphered protocol fields in the downlink of an LTE cell. By measuring the spectrum tendency of an LTE cell, we make several observations. For example, some metrics showing similar trend in the rough timescale of 1 hour have low correlations in 1 millisecond timescale. Different LTE data channels are used similarly in an hour for different packet sizes and TA values, but the MCS values in the previous time slot affect the channel occupancy in the next time slot. This is the end of my presentation. Thanks again for watching, and thank you for your interest in our paper.